Hello. In this collection of topics, we're going to be discussing the normal curve. It's probably the most famous distribution in statistics, and then the probabilities associated with the normal curve or the normal standard distribution. To begin, just to lead in, this isn't in the note packet, just a little brief intro. In prior chapters, we graphed discrete probability distributions using bar graphs. Now we'll begin to graph continuous probability distributions. Recall the difference between discrete and continuous is the following. Discrete are countable instances. They are whole number values. So if I was counting the number of socks owned, 2, 4, 6, 8, I can't have like 2.3. However, if I was studying the time spent studying, it could be theoretically any value between 0 and 24, since those are the number of hours spent in a day, and you can do parts of an hour. So that's the difference between discrete and continuous. Continuous is a continuous spectrum, and discrete are discrete exact points along the spectrum. In this section, we're going to begin studying the most important continuous probability distribution. Already hinted at that. It's called the normal distribution. It is used to model information in all types of fields: nature, education, health, industry, business, pretty much anywhere that you're going to be gathering data about a large collection of items, the normal distribution is going to pop up. The normal distribution, like I said, it's the most important continuous probability distribution in statistics. It's a graph of a normal distribution, has a variety of names. It's also called the normal curve or the bell curve. Properties of the normal distribution. The first thing is that the mean, median, and mode are all equal. They're in the center of it because, as item 2 is going to say, it's bell-shaped and symmetric about the mean. So the mean, median, and mode all occur at the exact same place. That's why it's so special. The total area under the curve is equal to 1. The reason why is because this is going to represent probability. And then the largest that your probability can ever be is 100%. The normal curve approaches but never touches the x-axis as it extends further and further away from the mean. The reason why is because even though these represent probabilities, your probability can never get all the way to 1 or diminish all the way to 0. The fifth feature is that between the mean minus 1 standard deviation, so the mean being in the middle, subtract 1 standard deviation, I'm right here, and the mean plus a standard deviation right here, the graph curves downward. It means from here to here it's curving down. It's kind of like a downward bowl. This is just going to the right. This is a downward curving portion to the left. The graph then begins to curve upward past to the left of the mean minus the standard deviation. So the left of this, it curves upward. So this is now curving upward, like an upward bowl. And to the right of the positive 1 standard deviation, it also curves upward. The point at which the curve changes from going downward to upward we call inflection points. That's really a calculus rule. It's where it's going from concave down to concave up. But it really, that little point where it switches, that tells us where the first standard deviation is. A normal distribution can have any mean and any positive standard deviation. It can have any mean because you could have any average. It depends on what you're studying. The standard deviation just tells us the spread of the data, how closely the data are grouped around the mean. The standard deviation, though, has to be positive. So whereas the mean can be negative, the mean could be negative because maybe we are studying weight loss, and people, if you're talking about a negative gain, that would be losing weight. So maybe the mean might be negative. But standard deviation is always a spread. It has to be positive because it's a distance really away from 0. The mean gives the location of the middle, the line of symmetry. The standard deviation, like I said, describes the variability or the spread of the data. So if I look at a couple following pictures, these first two, they both have the same mean. Their peaks are centered at 3.5, so their average is 3.5. This one over here is more spread out, though, A. So that's why I see it has a larger standard deviation. Its standard deviation is 1.5, whereas B's closer. The peak is, there's a lot more points closer to the mean. It has a smaller standard deviation. It has less spread, less variability. If you look at B and C, they both have the same standard deviation, so their spread is the same, but the difference is that their means are located just at different points. So that's how the mean and standard deviation play a role in the graph of a normal distribution. Just a couple examples of being able to read normal curves based on pictures. So a couple pictures for you. Let's look at A. The mean of A looks to be centered on 15, so its mean is 15. If I find where the peaks change from maybe downward to upward. It's hard to exactly say, but maybe somewhere like right in there. So probably somewhere between, about halfway between 15 and 18. Halfway between 15 and 18 is going to be, what, 16.5. So that means the standard deviation for A is about 1.5. Now I can do B. Actually, I'll leave these in here just to show. B, its mean looks to be centered around 12. Its standard deviation, again, a little difficult to say. I would mark it for you on an assessment or something like that. But appears to probably be around there. I'll use purple. Looks to be about 3 each way, so maybe I'd say the standard deviation is 3. Which one has a greater mean? The mean for A is definitely larger because the mean is 15. It's centered further to the right. Which curve has a greater standard deviation, the more spread? That's certainly B. B is far more spread out. Just an example of where standard deviation, or where the normal curve starts to get used. The average height of women in the US is 5'5", 65 inches, with a standard deviation of 3 inches. Sketch the normal distribution for this. Take number line, we're going to sketch in a normal curve. Done so following. If we know the mean is 65 inches, we're going to put 65 as the center. We know then that point of inflection is 1 standard deviation away, and each standard deviation is 3 inches. So I'm going to add 3 going to the right. So this would be 68, then 71, then 74. If I go to the left, I'm subtracting. This must be 62, 59, 56. And that's what the normal distribution would look like for the average height of women in the US. I'm going to give you a chance to try. The scaled test scores for the New York State 8th grade mathematics test are normally distributed. When you have a large sample, and usually it's a test, you tend to get normal distributions. The normal curve shown below represents the distribution. Estimate the mean and standard deviation, then use both along with the empirical rule to estimate between which two scores 68% of students score. Give it a try, pause the video now, come back and see how you did. What you should have found is this. You should have found, because the curve is normal, the middle is going to be the average, and the middle is 675. One standard deviation is 35 points away, so you can estimate that the standard deviation is 35. And then using the empirical rule, we know that you capture 68% of the data if you go 1 standard deviation to the left and 1 standard deviation to the right. So that means if I take 675, add 35 to it, I'm going to be at 710. If I subtract 35 from it, I'm going to be at 640, which means I know that 68% of students are going to score in between those two values. That's what allows me to eventually calculate percentiles. When you've gotten like your PSAT back and they said you scored in the 75th percentile, this is essentially kind of what they're doing. They're determining the ranges based on a normal distribution. However, the empirical rule has some limitations, as we're going to see. What if we wanted to know the percent of scores that are more than 1.5 standard deviations above the mean, or more than 2.2 standard deviations below the mean? Why is the empirical rule not equipped to do this? Why is it a failure? The reason why is because the empirical rule only allows us to estimate when we are concerned about whole number standard deviations. So 1, 2, 3 away. It doesn't allow us to do parts of a standard deviation. So in order to do that, what we're going to have to do is we're going to have to scale back to what's called a standard normal distribution, just to calculate how many standard deviations away a measurement is. And then we can use a table of values that are predetermined to state how many, what the percent is that is left than that number of standard deviations, or right of that, or in between two standard deviations. So there are infinitely many normal distributions, as we've seen. You can have any mean and any positive standard deviation. However, all of them can be converted back to what we call the standard normal distribution. The standard normal distribution is a normal distribution where we say the mean is at 0 because it is 0 standard deviations away from the average, and each standard deviation to the right is positive. If you're 1 standard deviation to the right, you have a value of 1. If you're 2 standard deviations to the right, you have a value of 2. As you head to the left, the number of standard deviations is just negative. we can then calculate what we call the z-score to be how many standard deviations away you are. And we did this back a few chapters ago. The z-score is simply the value minus the mean. This tells me how far away I am from the mean. And then if I divide by what one standard deviation is, it will tell me how many standard deviations away I am. So this is simply, the z-score is simply the number of standard deviations away a value is from the mean. If it's positive, that value is above the mean. If the z-score is negative, that value is below the mean. Just a brief side note about transforming to a standard normal. If each data value of a normally distributed random variable x is transformed into the z-score, the result will be the standard normal distribution. All we're really doing is we're not really changing the shape at all. We're just renaming the scale. So for example, with that height of women, if I retransformed that normal distribution that we took before into a standard normal, the only difference is 65 would become the number 0. Why? Because 65 is 0 standard deviations away from the mean, because it's on the mean. 68, let's do a different color, 68 would become 1, because it's 1 standard deviation above the mean. 71 would become the number 2, because it's 2 standard deviations above the mean. 62 would become negative 1, because it's 1 standard deviation below the mean. And 59 would become the number negative 2, because it is 2 standard deviations below the mean. All we're doing is we're rescaling the x-axis. That's all that a standard normal does. It allows me then to compare two items, like heights of women to heights of men or heights of children. Or it allows me to compare like what's more impressive in a track event. Is it more impressive to run this 400 or to jump this high jump? Well, I could compare how many standard deviations away each of those are from their average. Properties of the standard normal distribution, we've kind of already mentioned a couple of these. Cumulative area here means area to the left of that z-score. So when we state a value, we mean value to the left. The cumulative area is about 0 for z-scores that are close to negative 3.49. So if you're at negative 3.49, you're over here. What probability is it going to be that you're to the left of that? Essentially 0. It is very highly unlikely that you're to the left. You're more than 3.5 standard deviations below. The cumulative area increases as the z-score increases. So as you move to the right, we get more and more and more of the probability, because we're talking about area to the left. The cumulative area for a z-score of 0 is a half. If you're at the mean, it means 50% of the values are going to be left of you. The cumulative area is almost 1 by the time you hit 3.49. So by the time you're 3.5 standard deviations to the right, almost everything is going to be less than that. So those are just some basic properties of the standard normal distribution. There are two ways to calculate the areas for normal curves. One is to use a table. The second way is going to be to use a calculator. So we're going to show an example of using the table. So let's say you find that some value occurs with a standard deviation of 1.15. So right here. So its z-score is 1.15. It is 1.15 standard deviations above the mean. The question is, what's the probability of having something left of that? Well, if I go to a standard normal table, and this is found in table 4 in appendix B in your book, this is how you do it. On the left-hand side, it has the z-score out to the tenths. To the right-hand side, it has it at 100. So if I wanted to find the probability or the area to the left of a z-score of 1.15, I go to 1.1. Then I find the 0.5, because together these make 1.15. I find where they intersect, and the probability is 0.8749. So that means the area to the left of this z-score is 0.8749. I don't know why my pen's dying on me. 0.8749 is that value right there. That's how I can use a standard normal table. Instead of using a standard normal table, I can also use a calculator. So I can use a TI calculator, and it's built to do this. If I want to find the area to the left of 1.15, here's what I have to do. I have to enter, I go to second distribution, and there's a aspect called normal CDF that we'll use. You have to tell it the far left point and the far right point. Well, if you want to know the probability of being to the left of some value, the furthest left, we could go all the way to the left. So we just pick a really, really large negative value. So in this case, I believe I said like negative 1,000. Come on. So I just said you can pick some value way off here to the left. So all the way out here, maybe at negative 1,000 would be fine. All the way up to the right bound. So this first number is the left bound. This number is the right bound, 1.15. This number is the mean, and this number is the standard deviation. In order to get to it, I go second distribution, and you'll see it's option number 2. I hit enter. The lower bound, even in this, it's if you have a TI-84, it actually sets the lower bound to be something really, really large. This is -1 times 10 to the 99th. E stands for powers of 10. So this is way to the left. That'll be fine. You just need some value, because by the time you're -3, you're almost far enough. The upper value is 1.15. Because we have a mean of 0 and a standard deviation of 1, since we're the standard normal, we're good. We hit enter, and there's our probability, 0.8749. Same exact probability that we had before. Note, this tool now allows us to state the percent of values that fall between any two z-scores. Before, the empirical rule only allowed us to state the percent that fell between 1 or 2 or 3 standard deviations from the mean. So that's really the power of the normal distribution. So find the following areas under the standard normal curve. So what's the probability, or what's the area to the left of -1? So I already told you where you can go to find this. Hit second distribution, and then choose option normal CDF. So second distribution. I think I said 1, but it actually should be 2 right here. Lower bound, upper bound, mean. So in this first case, it's going to be normal CDF. The lower is just pick a big number, -1,000 is fine. -1, 0, and 1. And I'm going to run it. So that all the way up to, we said -1. These are the same. And run it. When we do that, you get about 0.159. It's about 16%. So 16% of values are going to be to the left of 1 standard deviation. What's the probability, or the area to the right of 1.8? What's the probability you're more than 1.8 standard deviations away from the mean? Again, grab a normal CDF. The left bound in this case is 1.8. What's the farthest right I could go? I could go all the way to 1,000 or more. 0 and 1. Grab my calculator and run it. So second distribution, normal CDF. This one we said was 1.8 for the lower bound, the left bound. The upper bound is just pick a big number. I mean, 100 would be fine. 0 and 1. And run it. 0.0359, so 0.036. So there's about a 4%, 3.6% chance that you're more than 1.8 standard deviations above 1.8. What's the probability you're in between -0.5 and 2? So I grab normal CDF, far left bound, -0.5, right bound, all the way up to 2, 0 and 1. Find what the probability is, or the area, because these areas represent probabilities. Second distribution, normal CDF. Far left is -0.5. Far right is all the way up to 2. My mean is centered at 0, 0 standard deviations away from the mean. 1 standard deviation we're calling 1, because it's a standard normal. Oh, let's type something. What? Try that again. Not quite seeing what the error is. Oh, I think I hit subtract. It needs to be a negative. -0.5. There we go. Enter, 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 enter. There we go. Yep. 0.669. So about a 67% chance you're in between those two z-scores, or that's the area in between those two z-scores. Can give you a chance to try. Find the following areas under the standard normal curve. What's the area to the right of 1 standard deviation? What's the area that is to the left of -2 and to the right of +2? You might have to be a little creative on how you find the second one. Pause the video now, come back and see how you did. Okay, for the first one, this is how you'll do it. So just type in normal CDF For lower bound, left bound is 1 all the way up to 1,000 or whatever. Pick a big number, 0, 1. You run that, you're going to get the following percent. So that's 16%. We've done ones like this before using the empirical rule. We could have done this one with empirical rule. This one on the right, the way to do it is find the area of one of these and then double them. So let's do this one to the left. So I'm going to find this and then just simply double it. So I'll do 2 times normal CDF. The lower would be negative, 100 would be big enough, all the way up to -2. Standard, so 0 and 1 for the means, 1 standard deviation. Find this area, double it, and then you're going to get that value. So that's how you'd have to do one where it's split like that. That is it for today. That's the introduction to normal curves and calculating the areas under the normal curve, which will represent probabilities going forward. Thank you very much and have a good day.